Okay, now we're ready to go. And let's look at where we were yesterday. Okay. I think we had just finished this, but I'll just click through it quickly. We're going to build electron configurations for atoms, and what that means is we're going to specify the particular orbital and particular space within that orbital where the electron is located. We're going to give the 4 quantum numbers for each electron that will uniquely define and identify that particular electron. And we have to do that in a particular pattern. Now, you might say, well, why don't we just use the Schrodinger equation and solve that equation for a large number of atom electrons, electrons and atoms? Well, we can solve hydrogen absolutely perfectly. And like I said, everybody would believe the results of the quantum mechanical model for hydrogen, even if they got an experimental result that was opposed to it. Nobody would believe it. And it's the one case that I can think of where the theory trumps experiment. It's never that way in anything else, because you try a theory, and if the experiment agrees with you, okay, good. But if the experiment disagrees with your theory, your theory is wrong. And so this is the one great success that quantum mechanics has had. Now you'd say, okay, well, let's do helium. Well, helium, we can't even do helium exactly. Now, if you put 2 electrons in, see, in the hydrogen case, the model was easy to model because the hydrogen had only 1 proton and 1 electron. The only forces between the 2 are the electrostatic forces that vary as you change the distance. And we could create a model that modeled that exactly. However, if you put 2 electrons in, then you've got a problem. Each electron behaves just like the hydrogen electron did toward the nucleus. But electrons, remember, they're moving very fast. Inside an electron orbital, they are moving probably fractions of the speed of light. So the electrons are moving very rapidly inside the atom. Also, remember, the electron can be modeled like a wave. And in that sense, each electron is occupying the entire volume of that orbital that it's in. And so it's impossible to take into account the electron-electron repulsion. And electrons do repel each other. So when one electron is some point in the atom, the other electron experiences it no matter where it is. And since that changes with the speed of light almost, there's no way that you can make an accurate model. Now, people have done some things that they thought might work. Since electrons repel each other, if one electron's on one side of the nucleus, the other electron's exactly the same distance on the other side of the nucleus. And when one moves up, the other one moves down. When they move to the left, the other one moves to the right. And they would do an exact correlation of the electrons. And that doesn't even sound like it would work, and it doesn't. The other one that worked a little bit better was they just imagined that one of the electrons has traveled and occupied the whole space and becomes like a spherical charge of some diameter. And the other electron is treated like a little particle moving in the experience of that spherical charge of the other electron. And, that works a little better, but it still doesn't give a correct prediction of the energy levels and spectrum in hydrogen. So there's really no method that's direct. We have to go to an approximation method. And we've got some approximation methods that really work well. In fact, the truth of the matter is we have quantum mechanical models now that, though they're not exact, they can give you several significant figures on the energy of any atom or molecule. In fact, we can create a model of the electron distribution in very, very large molecules of the size of enzymes and things like that. So we can do very good. We can do very well with those models. But for the most part, they're way too expensive and way too much time. You have to have a really good computer. I don't know if you know about computers very much, but MTSU's we offer a PhD in chemistry in computational chemistry, and the computer they use is a 32-node parallel computer that is very comparable to the big supercomputers that you might find anywhere else. And they can build models like that, and you can put on the 3D glasses and look at your computer screen, and it'll display a molecule, and you can reach out with your hand and grab on one of the atoms and turn the molecule around and look at it from either perspective you want to. It's really cool. But anyhow, we are going to try something different. The idea was, okay, we've got exact energy levels for hydrogen. We know where every single one of them is, and we can calculate the exact energy of every level in hydrogen. And so we assumed that if I just put another proton in the nucleus to make helium, well, the two protons are always locked together, so that shouldn't matter. It's the second electron that we have trouble with. So what we do is we put the second electron into the orbitals that hydrogen had, and then obey a couple of rules and figure out what we call the electron configuration for that new element. So if we do that, we get a pretty good model. Now, we do need to take into account something called screening, and it was sort of like what I told you a while ago, assuming the first electron goes in, creating some kind of a spherical shell of charge that's negative. If you look at the electron that's way out there, you're trying to put that second electron in, looking at it, the nucleus might have a +2 charge, but because of that spherical, someone's got your mic on. Okay. Because of that spherical charge of the first electron, the outside electron doesn't really feel a +2 charge. It feels a little less charge than that because that inner group of electrons under it are screening it from the nucleus. So it doesn't feel the full nuclear charge. And so we can take that into account and imagine what happens, and we'll see some periodic trends in that. Now, the time that an electron spins in some region of space depends on the number of nodes that that electron has. You can imagine that if you look at an electron in an orbital, if that orbital has no nodes in it, that electron can go right into the nucleus. And we talked about that. That's the s orbitals. They all have maximum intensity for the wave function at the nucleus, and it drops off and may go through some other nodes before it gets to infinity, depending on whether it's the 1s or 2s or 3s and so forth. But all of those electrons penetrate right into the nucleus. And so they can interact with the nuclear charge. But if I'm looking at a p orbital, remember the p orbital was like a dumbbell shape, and it had a node at the nucleus. Now that means the p orbital electron is forbidden to go into the nucleus. It can't get in there. And so it can get close and it can experience the charge, but when it has a node in there, it's not going to be affected by the nuclear charge as much as, say, it would be in an s orbital. So that can give us a pattern for the screening. S orbitals have no nodes, and p orbitals have one node, and d orbitals have two. So the electrons outside is not going to feel that as much. So you've got S and P and D and F as the order of the screening is in the same way that the nodes appear. Okay. Now, the other rule that we're going to look at is that the 4 quantum numbers identify an electron. And so no 2 electrons in any atom can have the same set of all 4 quantum numbers. That would be like trying to park the same 2 cars in the same parking space. It just doesn't work. Well, the same thing is true for electrons. No 2 electrons can have the same exact point in space where they're located, and that means one of the quantum numbers, sometimes just the S quantum number, has to be different. You remember yesterday when we did all of the quantum numbers for n equal 3, I think, and they did appear in pairs. All of them had a pair of quantum numbers where the only one changed was the spin went from +1/2 in one to -1/2 in the other. Okay, so this is the Pauli exclusion principle, and we just have to make sure we don't do that when we're building electron configurations. So 2 things to worry about or to consider. The value of N plus L is the overall energy level. And as N plus L goes up, the energy goes up. And we're putting electrons in, we have to be careful we don't give any 2 of them the same set of quantum numbers. Okay. Now the K shell is made of just one component. N is 1 and L is 0. It's called the 1s orbital. The L shell has 2. It's the 2s and the 2p. Now what I've drawn here is I've put 3 values. That's for the p. One of them is the p along x, the other one's the p along y, and the third one is the p along z. And so there's 3 of them. They have the same energy unless there's a magnet around. If there's a magnet around, remember the p orbitals have a magnetic moment as well. It's an orbital motion that has L equal to 1. So it would split into 3 levels in the presence of a magnet. For example, if I brought a magnet up and an electron was in this orbital, what would happen is this plus quantum number would go down and this minus quantum number would go up, and the spacing between the 3 levels would be dependent on the strength of the magnet you brought up. If you had a real strong magnet, you get a big spacing. Weak magnet, less spacing. With no magnet, they all 3 are the same energy level. But that makes up the L shell. When we go to the M shell, 3s, 3p, and 3d is possible now. And again, the reason why there's 5 here, these are the M sub L values, by the way. L is 2, so we go from +2 to -2. We're going to fill this left to right because we're going to do positive quantum numbers always before negative. And so this is the order. Be sure you pay attention to that because some people do it differently. That's not a big deal. In Europe, they drive on the wrong side of the road, for God's sake. Not wrong to them, but it seems it certainly is wrong to you if you drive on the side of the road we do. Here, you're getting a bit of a problem. 4s, 4p, 4d, and 4f. So we have the next shell would be the n equal to 5 level, and 6, and so forth. And we're generally not going to get all the way to the top of this distribution in any atom on the periodic chart. So every element that's on the periodic chart, we can do its electron configuration by putting them into this pattern. There are some tricks to doing this and creating this pattern. I don't think it's worth bothering with any of them, because very shortly we're going to abandon it anyhow and write electron configurations a different way. In fact, before we finish this discussion, we'll be using a slightly different way of doing this. Okay, so let's think about building electron configurations. Okay, we've got hydrogen. Now, hydrogen is the first element on the periodic chart. It's got 1 proton and 1 electron. So I only have to put 1 electron in, and I've ranked these in order of energy from lowest to highest as you go up. But I've separated out the orbital types to make it a little easier to see. Now think about it, on the atom itself, all of those are stacked over each other. So you need to push all of these over to the left and make one stack, but it would be hard to follow. This is much easier. So I'm going to put 1 electron into the 1s orbital, and notice I've used an arrow because I can do 2 orientations with an arrow. This one would be pointing up, so that'll represent the electron, and as we agreed, the electron is going, the quantum number for that electron is going to be positive for all of them, and the only one we need to worry about now is the spin. So the hydrogen electron has a spin plus 1/2. So I can generate the orbital designation then is the 1s orbital with 1 electron in it. And we say that 1s1. It's quantum numbers. N is 1, L is 0. Now you might want to put this little table out somewhere, just number 0, 1, 2, 3, 4, 5, and then under that you write S, P, D, F, G, H, I, K under that, so that you realize what the quantum numbers are for each one of these values are. So I don't show an m sub L value on s orbitals because it's 0. It doesn't have a plus 0 and a minus value like I did up here. You see in the p orbital here, L is 1 for p orbitals. So I go plus 1, 0, and minus 1. Up here in the d orbitals, L is 2, I go plus 2, plus 1, 0, minus 1, and minus 2. So this electron has 4 quantum numbers. N is 1, L is 0, M is 0, and spin is up, plus 1/2. So that's the orbital designation for hydrogen. Now let's do helium. If I'm going to do helium, helium has 2 protons in the nucleus. It's element number 2 on the periodic chart. And that means it's got 2 electrons. I need to put a second electron into this one to get helium. Where does it go? Well, it's going to go in the lowest available orbital. Now, it could go here. We could say, okay, we put 1 here and 1 there. That would be okay. The only difference is it's competing with 1 here and 1 here, spin down. Now, the one that is chosen is the one of those 2 configurations that is the lowest amount of energy. The 2 electrons do repel each other. So when I put the second electron into that s orbital, it's going to be repelled by the first one. So that's energy that is in repulsion. But it's going to be attracted by the nucleus, and that's going to be attraction. So the overall energy for one electron here and the other one here with the spin down is lower than one here and one up here with spin up. So nature chooses this one because this gap is pretty huge. Remember in hydrogen, the difference between this gap and this gap was the ultraviolet line in the hydrogen atom. And so this is the orbital designation, and we just write it out, 1s with 2. Now you say it that way too. You say 1s2. You don't say 1s squared. It's 1s2. Okay, so it's got 2 electrons in the s orbital. I'm almost putting this new one in blue so I can focus on which electron we're writing the quantum numbers for. Okay, let's see if we remember. That's n, L is 0, M is 0, spin is -1/2. That's what we get, right? The first electron we did was 1, 0, 0 plus 1/2. This second one, the blue one, is 1, 0, 0 -1/2. The only thing that was different is the spin of the electrons. One spin up, one spin down. Lithium would add one more electron to this configuration to get lithium. Lithium is element number 3 with 3 electrons. Where would it go? Well, you could say, okay, all these orbitals are available, but this one's lower in energy. Now again, why is it lower? N is 2, L is 0, 2 plus 0 is 2. N is 2 here, but L is 1. 2 plus 1 is 3. So N plus L is greater for this orbital than for this orbital. So these 3 are all going to be higher in energy than this one. So there's no question the next electron is going to go here. Now, what's this going to look like? Well, I'm going to introduce right now the new way we're going to use for writing electron configurations. That 1s2 that we put in here was the orbital designation for helium, and helium is extremely, totally, absolutely unreactive. It never makes a compound with anything under any set of conditions. So that represents a very stable arrangement of electrons. It doesn't want to change that arrangement of electrons. So we're going to, instead of writing the 1s2, since that's one of the noble gas configurations, we're just going to put that He in brackets. Now, what this is remember when we talked about where we were going, I said our model for the atom has a nucleus in the middle, and then it has electrons around that nucleus that form a core of electrons. And the other electrons outside the core are the ones that give rise to chemical reactivity. And so those electrons outside the core are the valence electrons. And in this particular case for lithium, it's going to have this spherical core that is exactly like helium. And then it's going to have one electron in addition to that in the 2s orbital. Now, lithium is in group 1, remember? And all of group 1, you remember what the charge was for all of them? It was +1, right? If you see here, there is a 1 electron sitting out there all by itself. Right under it, there's a perfect core of electrons, helium. So is it surprising at all that this element would like to lose that electron, get rid of it totally? Then the lithium +1 ion that is produced would behave and look just exactly like a helium atom, except, of course, it's got an extra proton in the nucleus, but hey, who cares? That's not important for the chemistry in the nucleus. What's important is the arrangement of the electrons. So it's not surprising that all group 1a elements, and this one we see immediately, will lose that electron and be left with a noble gas core. And we're going to see that as we build this pattern for other elements. So in this one, instead of writing the orbital designation 1s2, 2s1, the 1s2, I'm going to write He as a core to remind myself it has a noble gas core plus 1 electron. That gives me an understanding of lithium having only +1 charges in all of its compounds. Okay, so the orbital designation is the helium and 2s1. So that's lithium. Now, the last electron I put in is going to be this one. N is 2, L is 0, M is 0, spin is +1/2. All right, let's do beryllium. Now, beryllium, this gap is closer together. See, N is the same number. So N is the principal energy quantum number, but L does have an influence. So there is a spacing between these two. Now, if I put the second electron in with this one, it's going to be repelled by that one. It doesn't really want to go there if it could. But it turns out the spacing is still too big. Putting the electron here is a better arrangement than putting it here because it doesn't have to be repelled by the other electron. If I put it up here, that energy gap is bigger than the repulsion energy here. So the electron goes there. Now, if you remember when we talked about the unreactivity of hydrogen, we said, oh, okay, if I had all of that orbital full, then maybe that was a stable configuration. Well, if you took that same argument to this point and said, okay, this orbital is full and this orbital is full, therefore beryllium would be a noble gas. Well, you know it's not. So it's not the fact that the orbital is filled. It does turn out, though, that filled orbitals like this versus partially filled orbitals like having one here and here, the filled orbital is more stable than the partially filled orbitals, putting one electron and one here. So the lower energy is still going to be filled orbital instead of a filled one and 2 partially filled ones. So beryllium is going to be a helium with 2 electrons in that outside in the valence shell. Remember what charge we said group 2 had? That's right, +2. So you see why? We've got this pair of electrons. If I take them away, what's left is the helium core again. So if I take 2 electrons from beryllium, it sort of looks like helium if helium had four protons in the nucleus. It doesn't, it's just got 2. All right, moving right along. Quantum numbers then for that blue electron. Here, there's N, 2. There's L, 0. M is 0. Spin is -1/2. Now boron. Okay. Yes. You have a question?
Yeah. Why for the beryllium? I'm confused because I don't understand where you're getting the L equals 0. Do you mind going over that?
I'm sorry, I didn't quite catch you. Let me turn my volume up a little bit.
For the L shell,
yes.
you just said for like the N equals 2, L equals 0. I'm just confused because in the L, there's like the 2 arrows. So do you mind going over how you got that number?
The value for the quantum numbers?
Yeah.
Oh, yes. We're going to do that right now. We're going to put this electron in here. And now I'm going to focus on this and I'm going to answer your question right here. This electron, N is 2. This electron is a p orbital, and for p orbitals, L is 1. The M value is this one here, and the spin is up. So N is 2, L is 1, M sub L, or M is +1, and spin is plus 1/2. So this is the orbital designation, helium, and it's 2s2, 2p plus 1 with 1. Now, please do put that plus 1 on. A lot of people don't do that, and I've got a real good reason why I want you to focus on that. So we're going to give orbital designation. We would say helium, 2s2, 2p plus 1, 1, and spin is plus 1/2 for this one because the first one that goes in is plus. Now, why did I put it here? Why not here? Or why not here? It's just like we said. In this country, we're going to drive on the right-hand side of the road. In Europe, they drive on the left-hand side of the road. Both people, both countries, that works. And the rule is going to be assign positive numbers before negative and before 0. So instead of putting the electron, say, over here in the 0 orbital or in the -1 orbital, I'm going to put it in the +1 orbital. Now, really, the reason for that is that when you bring a magnet up, the plus one's stabilized by the magnet if the North Pole is brought up, and the negative ones are destabilized, go higher, if you bring a North Pole up close to the magnetic field. So taking the North Pole of a magnet to be plus magnetic field, this +1 quantum number is going to be the lowest when the magnet's present. And that's where that electron would be if I brought a magnet up. Okay, let's do carbon. Now, it is pretty clear. These three all have the same energy without a magnet around. And so that means that if I put that blue electron over here and spin pair it, so it would have to go spin down if I did that, the two electrons would repel each other a lot. But if they're over here in this m sub L value, then the electrons, there is a node between this one and this one. And the electron in the +1 m sub L orbital and the electron in the 0 m sub L orbital have nodes that prevent the electron from one of them to experience the other one. There's a node between them. They don't repel each other. So putting that second electron doesn't destabilize the orbital. Instead, it now becomes very stable. And now we've got two spins, +1/2 and +1/2 here. And if I bring a magnet up to this guy, that splitting is going to get twice as much because it's involving two electrons. And so the three orbitals would separate. And what would probably happen if you put a real strong magnet up, this one would go way, way down, and this one would go in the middle. The 0 would stay where it is, and the +1 would go up here. And if you get that magnetic field high enough, that electron here would drop down and pair up with this one. It would go down here in a real strong magnet. But in the absence of a magnetic field, all three of these levels are the same. So it's a better arrangement to put one in each of the two orbitals before we pair them up. Now, there was a little general rule that was that explained this. They called the Hund's rule, was that when you have different configurations possible, the one with the maximum spins would be the most stable. And so you would put electrons in unpaired as long as you possibly could. And then, for example, the next electron that's going to go in would go here before it starts to pair up. And then once all three of these pair up, the next one has to pair back up. You'll see that in a minute. So for carbon, this element, now, if I looked at this configuration, how could I tell that's carbon? 1, 2, 3, 4, 5, 6. That element has 6 electrons total. And if you look on element number 6 on the periodic chart, it's carbon. Or if I just had carbon and I wanted to get the configuration, I could just do 1, 2, 3, 4, 5, 6, and I would know carbon had 6. They'd have to arrange like that. So what we're doing now is just going to the next element every time. So it's a little easier to do that like that. So now, so this is the orbital designation for carbon. And if you look at carbon, it does have, you see right there, it has 4 electrons on the outside. It's group 4. One of its charges was plus 4. It's in group 4A. So one of its charges is plus 4. You see why? You take these 4 away, you're left with helium. One of its charges is also minus 4. So if I put electrons into this orbital, I can put 2 more and I would fill this up. And altogether, then there would be 6 electrons in that, in this part over here, plus the other 2 that we'd have here would be 10 altogether. But that we could expect the charges for group 4 to be plus 4. Now, if we look at this last electron that's added, the blue one, now let's look at how I get the quantum numbers for the blue one. There's the N value, that's 2. There's the L value, it's a p orbital. P orbitals, L is equal to 1. Remember I said, do that little table. Do 0, 1, 2, 3, 4 in a line, and then right under it, write under 0, write S, and under 1, write P, and then D, F, and G, and H, and so forth. And that'll help you avoid a mistake that I'm not going to mention because I've learned, and I didn't get this bald head I got and all these wrinkles without learning something. And as a teacher, I've learned never, ever teach what mistakes people make. It just makes more people make them. And if you think about it, it makes sense. Because if you remember something but don't remember it exactly, you remember something about it. What you remember the mistake that I taught. So I'm not going to teach mistakes. I'm going to try to kill them boogers. Okay. So this is what your electron configuration would look like for carbon. And I'm going from carbon, and if I want to go to the next element, I'd put an electron in here. And now this is by Hund's rule. It maximized the magnetic effect. You put an electron in each one of the orbitals before you paired it up. Remember, the magnetic interactions here between these unpaired spins. And there's one here, and one here, and one here. Putting the electrons like this gives me 3 spins to deal with. If I put this one in here and paired it up, this one would cancel. I would only have 1 spin to deal with. So magnetic field, excuse me, the magnetic field interaction is going to be the greatest with all of the electrons unpaired. So electrons remain unpaired, as Hund's rule said, as long as they can before you ever pair them up. And in a p orbital, I can put 3 in before I have to pair them up. And that's where they go. They go 1 in each one. Now let's get the quantum numbers again. It's in this orbital, that's 2. It's in this orbital, that's L, N is 2 and L is 1. The M sub L is this number here, it's -1. And the spin is up, plus 1/2. So I've got the 2s2, 2p plus 1 with 1, 2p 0 with 1, the 2p minus 1 has 1. Do not write 2p3. If you Google it, that's what they'll tell you. That'll be wrong, but that will be one of the answers on the test. Okay. All right, now, so the last electron again, 2, 1, plus 1, plus 1/2. Let's do oxygen. Okay, with oxygen, I put another electron in. It has to pair up somewhere. We are going to put it here always because it's putting it into a positive number. M sub L is +1. If I put it over here, still spin down like it would have to be, now I would be putting that extra electron in a 0 orbital. Or if I put it here, I'd put it in a -1. We have agreed positive before 0, before negative. So this is the orbital designation that we would use. We've got the helium core again. Remember, that's this part right here. Outside that core, well, I'm sorry, helium right here. Outside that core, we've got a 2s with 2 in it. And then we got the 2p + 1 with 2. And then the 2p0 with 1. And the 2p - 1 with 1. So that is the orbital designation for oxygen. Again, oxygen could lose all 6 of these electrons. It's in group 6a, and the elements at the bottom of that column do form, metallic ones do form a +6 charge possibly. Oxygen really doesn't, but technically it could. How could it be? Look at this stable. How could I make this stable? I could put another electron here and another electron here. Then I would have all of these filled, and that would be a stable arrangement. So the other charge of group 6 is -2. I can have +6, add another electron there, that would be -1. Add another electron there, that would be -2. And so the charges are +6 and -2 for group 6. This is why. So look at our last electron again, the blue one. It's 2, 1, +1, -1/2. So that would be the quantum numbers for that electron. Suppose, hey, I don't know, I'm looking at this and I'd say, okay, that's the last electron. What would be the quantum numbers of the one just before it? The next to last electron that was added? Well, it would be this one right here. It would be this one. And its numbers would be what we got a while ago. 2, 1, -1, +1/2. So we can just pick out any electron we want to. That one right there. 2, 0, 0, -1/2. So we can get the orbital quantum numbers for any one of them. If I do fluorine, I'm going to put one more electron in. I've got a space here and here. Where's it going to go? In the 0 before the minus. So it's going to go here. And it has to spin pair because I can't have any 2 electrons with the same set of all 4 quantum numbers. If I tried to put this one in with spin up, then both this electron and this one would have the same set of 4 quantum numbers, violating the Pauli exclusion principle. So what does the orbital designation look like? Well, it's helium. Then that's S. Then we got a 2s2. That's there. We got a 2p + 1 with 2. That's this set. We've got a 2p0 with 2. That's this pair. And we got a 2p - 1 with 1. That would be this guy here. That's fluorine. And it's in group 7. And sure enough, there's 7 valence electrons. I could lose all 7. Fluorine's never going to do it. But I could lose all 7 and go back to the helium core. That would be a possible charge for the elements of group 7. Okay, but a more likely charge is to put an extra one in here. That way I have all these orbitals full. And if I did that, I would have a -1 charge possible for fluorine. And group 7, the ones near the top, are most always -1. Fluorine is never anything but -1 in its ionic compounds. and the quantum numbers for the fluorine electron is obtained the other way. Now, the next one is the next member of the noble gas family. And neon also is totally unreactive and never has reacted with anything. Well, again, now it's got the K shell full and the L shell full. So we might think, okay, it wasn't just orbitals being filled, although I have said, and it is true, that filled orbitals and empty orbitals, by the way, mathematically, those are the same. You know, it's like a plus and a minus, you know. The only difference is that. But um, the all of the orbitals are full, but when we just got to here and had the orbitals full, it wasn't a noble gas. That was beryllium. We get to here and have the shell filled and this shell filled, we do get a noble gas. So, okay, maybe that's the answer. So the orbital designation, we're going to write it first like this. And now, anytime an orbital is completely full, that's the one time you can write it 2p6. Remember I told you when we did the 2p3 is wrong. You had to show the split out of where the electrons are located. When an orbital is completely full, it's not going to contribute to the chemistry very much of that element. So it is okay to show the 2p222 as 2p6 because that's 6 electrons that fills the orbital, and this one is a noble gas. And it does have electrons out there in the valence region for it. Excuse me. But it is totally unreactive. Okay, now, last quantum number, okay, 2, 1, minus 1, minus 1/2. Now, let's go to sodium. Now, sodium is element number 11. If I'm going from scratch, I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's where that extra electron is going to go is here. Now, since this whole region now was the neon core, and neon was totally unreactive, instead of writing the sodium as the helium core and then 2p6 and then 3s1, that noble gas core, I can take care of all of these 10 electrons just by writing neon as the core. If I wanted to know what that was, I could break up neon and put in what we had a while ago, 2s2, 2p6. And if I wanted to go all the way to the complete designation, I could break helium back up to 1s2, and then I'd have it 1s2, 2s2, 2p6, 3s1. But this is better for us because it does illustrate the chemistry. If I look at group 1, all of the elements in that group 1, lithium and now sodium, they have a noble core with 1 electron in them. So it does lose the 1 electron. So all of those elements in that same family have the same kind of electron designation. They have a noble core with 1 electron on the outside. And so the only thing that's happening is the core is getting bigger as I go down the column on the periodic table. If that, as I go from lithium, sodium is bigger than lithium. Potassium is going to be bigger than sodium, and rubidium bigger than potassium, and so forth. They get bigger going down, but they all look alike. They have one electron on the outside. Now think about, I told you that the properties of the group 1A elements are is you could take a lithium, you cut off a little piece, and you put it into water. It kind of sizzles and reacts, and it gets a little bit but exciting, but it sometimes doesn't even show a flame. But if I put sodium onto water, immediately the sodium gets so hot it melts. It sizzles and runs around all over the top of the water, and it's hot enough that the hydrogen that is produced catches fire. So you see a little flame running around all over the surface of the water. And potassium will catch fire and essentially explode as soon as it hits the water. Why is that? Well, the electron that's coming off when each one of them reacts is further away from the nucleus and easier to get out. And that means it's going to react faster and better to do that. And so this electron in sodium is much easier to remove than the corresponding electron in lithium. And when it reacts with water, sodium does it much more vigorously than lithium does. And potassium still more because it's still bigger. So all of this gives us some lots of information about the chemistry that we see on the periodic table. Now we can begin to understand it once we've looked at this orbital designation. Now, magnesium, I'm going to put another electron in, and sure enough, I'm thinking about this electron's going to come in where it's going to go, no, not here, it's going to go bloop right there. It's going to land in that one because that's the lowest available energy orbital for it. But it has to pair up as it goes in, so the spins pair of magnesium. The spin of a magnesium atom, electron spin of the magnesium atom would be 0. Yeah, all of its electrons are paired. If I go to aluminum, the next element on the periodic table, I put another electron in, and how many is that? 2, 4, 6, 8, 10, 12, 13. Aluminum is element number 13, and if I were building it from scratch, I could do it like that. I put the first 2 in here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's where I would put it. Okay, what would its orbital designation look like? Well, now remember, from the K and L shell make up the neon core. Beyond the core, then I've got 3s with 2 and the 3p plus 1 with 1. So the quantum numbers are 3, 1, plus 1, plus 1/2. Silicon. We put the next electron in. We've agreed we would put the first one in the positive quantum number. There is another level, m sub L value, another orbital where that electron could go at the same energy. So we put the first one in the positive number. The next one's going to go in the 0. And the next one, okay, you already see where it'll go. It's right there. So what are its quantum numbers now? Okay, 3, 1, minus 1, plus 1/2. Sulfur. It's 1 over oxygen. And if you remember what we had for oxygen, it looked just like this, except it was the 2 quantum numbers here. So again, the only difference between sulfur and oxygen to the outside world is sulfur is bigger. So if you think about adding electrons, that's what usually happens in that family, sulfur and oxygen. You gain 2 electrons. You can see that. We got places for 2, 1 here and 1 here, before we got everything paired up. Oxygen is much more vigorous a reactant than sulfur is in that way. Why is that? Because the added electron can get in closer to the nucleus in oxygen, because it's smaller, than it can when the electrons go in, when the 2 electrons go into sulfur. They're going to go into an orbital that's further away, and it's not going to release as much energy as it does when it goes in closer to the nucleus in the case of oxygen. So that's why oxygen is much more reactive than sulfur. Okay. Chlorine, I put one more electron in, and that electron would have to go into this one paired up, but and I put it there rather than over here because 0 is priority over -1. There its quantum numbers. Argon. Now, argon is also one of the noble gas families, and it has never been reacted with anything either. Again, we used to call them inert gases. But argon is inert, just like helium was, and just like neon was. You can heat them up to the temperature of the sun and mix them with anything on the periodic chart, and you won't get a compound. It won't work. They won't react at all. So this is as a stable configuration. But you know, a while ago we said, okay, maybe this noble character is because you have a filled shell and a filled shell. So filled shells might be it. Nope, look here. The 3s, 3p, and 3d make up the M shell, and it's not full. We don't have any electrons in the d orbital of the M shell. So it's not shells that make it up. I'll give you the hint right here. What I see here is 8 electrons on the outside of that atom. This one has 8 electrons on the outside. In neglecting helium, all of the noble gases have 8 electrons on the outside. And we used to teach a thing called the octet rule, and we still use it. That says when an element has 8 electrons on the outside, it's stable, and therefore all of the metals are going to lose electrons until they have 8 left on the outside, except lithium. Or they're going to gain electrons if they're nonmetals, and they'll gain enough to have 8 on the outside. And then that turns out to be a rule that does work in almost every case. So it's this 8 electrons on the outside. And you already know that the s orbitals are all spherical, right? If you took the 3 equations that make up the p orbitals and added them all together at once, instead of showing 3 separate p orbitals, if you do that mathematically and put them all together at once into the same figure, you come up with a sphere. So it is a spherical shape. Those atoms have a spherical shape on the outside, and that tends to be unreactive with 8 electrons on the outside. Again, real quickly, just to review, N is 3, L is 1, M sub L is -1, M sub S spin is -1/2. The next electron is to go in is potassium. Now, why did it go here instead of here? 4 plus 1 is 4. 3 plus 2 is 5. So N plus L is 4 here and 5 here. N plus L is 4 is lower in energy than N plus L equal 5. That's why this component of the M shell does not fill until this component of the N shell fills. And then we'll be able to go over here. So potassium is going to have now an argon core, and that's all of these electrons. So you see, instead of having to go in here and go 1s2, 2s2, 2p plus 1 with 2, 2p0 with 2, 2p minus 1 with 2, 3s with 2, 3p plus 1 with 2, 3p0 with 2, 3p minus 1 with 2, and 4s1. You get to that valence electron. We can take care of all of those electrons except the valence one just by writing argon as the core. And that still gives us a nice picture of group 1A. helium core with 1 electron for lithium, neon core with 1 electron outside for sodium, and now argon core with 1 electron on the outside for potassium. Now, the next electron is scandium. And scandium now, if you have a periodic chart in front of you looking at it, it's the first member of the first row of transition elements. Now, I want you to understand something. The size of the orbital is determined by the value of n. This orbital is bigger than these orbitals, but the electrons go into this one first because of the n plus L rule. So when I'm building the transition elements, the electron I'm adding is not on the outside of the atom. It fills after this one, but it's inside this one. So the outside of all of these atoms is the 4s2 configuration. Now that means that the added electron is not going to change the properties as much as the others did. When we're adding electrons in the outside layer of any atom, that very outside piece of the outside layer, maybe that's a better way to say it, that very last piece of the outside layer is a spherical orbital with 2 electrons in it. And so on the very outside, all those transition elements look the same. But I'm putting different numbers of electrons in the layer under that. So the properties don't change so rapidly. The ones where I'm changing the outside, we called representative elements. That's the 2 left columns on the periodic table and the last 6 columns on the periodic table on the right. Now we're building the transition elements, which have electrons buried under that very outside layer. So I'm going to put 1 electron in. Now, let's do our quantum numbers again for scandium. N is 3. L is 2 now. Remember the little table, 0, 1, 2, and for SPD. And so it is, L is 2 for d orbitals. And M sub L is going to be +2 for this one. And we put the electron in the positive number before we put it in any of the others. So its quantum numbers are going to be 3, 2, +2, +1/2. Now, if I follow the pattern, I'd go on over to chromium in the electron configuration. What we would expect for chromium is this. We would expect this 4s2 and 3d with 1, 2, 3, 4 in it, each one like that. That's what we would expect. Now I've made in big red down here that that's wrong. How do I know it's wrong? Well, if I'm looking at this, there are 4 spins, 4 electrons unpaired. We can tell the number of unpaired electrons in a metal really, really easily. You build a balance, and the pan and all the stuff right around where you put the element in to weigh it is made of plastic in this particular balance. It's called a gooey balance. Everything around the pan where you're going to weigh the object is made of non-magnetic materials that a magnet doesn't affect. And then under that pan, you put a strong electromagnet that you can turn off and on. And now you take a sample, for example, of chromium. Well, if I put an element in that had 1 unpaired spin in that element, and I put a mole of it on the pan to balance it. You know, the mole would be equal to the atomic weight. So I just take the element, put its atomic weight on the balance, and I weigh it. If I flip the switch and turn the magnet on, the magnet will pull on that unpaired spin in the electron. So every atom in there is going to flip over its spin, so it's attracted to that magnet, and it's going to be pulled into the magnet, and it generates enough of a pull that the weight appears to go up. And for 1 mole of unpaired electron spins, you always gain a certain amount of weight. If the element had 2 unpaired spins, the amount of weight it would gain would be twice as much. If it had 3 unpaired spins, the amount of weight it would gain would be 3 times as much as with 1 spin. So you can actually count the number of unpaired spins in an element just by weighing a mole of it on a GUI balance and compare that to the weight change that you get for that one with one that's known to have 1 unpaired spin. And you do count the number of spins that way. When you do this for chromium, you don't get 4, you get 6. So that means that this electron doesn't have the configuration that I'm showing you. It's got to have one that shows 6 unpaired spins. There's 2 electrons that spin. If I took that one of them away and put it over here, that would explain what I've got. I would have 5 here plus 1 here, and that's exactly what we think chromium does. That electron moves from there back to here. And so now I've got 1, 2, 3, 4, 5, 6. Again, remember when I put an electron into these orbitals, the first one that goes into any orbital has spin up, spin plus 1/2. So I do have 6 unpaired spins, and that is what we observe. Now let's see if we see something in a pattern here. I told you filled orbitals and empty orbitals are treated mathematically the same. And so the other configuration I'm seeing here, when I had 2 electrons here, I had a filled orbital. That was good, but this one was not filled. And it was not empty. But if I move an electron from here to here, look at what I do have. I have a half-filled orbital here, and the d orbital has 5 in it. Each one has 1. That's half as many as it could have. So the order of priority generally are filled and empty orbitals are the best thing to have. And then half-filled orbitals are next best. So this is the next best thing, and it's better than them being paired up here and empty one here. So chromium and all of its family have this configuration where an s electron moved into the d orbital to give a half-filled shell here and a half-filled shell here. Everything in that family does that. And by the way, almost every standardized exam that I've ever looked at on freshman chemistry asks for the number of unpaired spins or something like that in an element in chromium's family. So you need to remember that. When you're doing the electron configuration for chromium or anything in its family, it's going to have 6 unpaired spins, and you have moved an electron from an s orbital into the next or to the next available d orbital in order for that to happen. So that happens at chromium. Now, if we continue to go across the periodic chart, we would, oh, okay. And now, if you continued on the periodic chart, you do the same thing. Then after chromium, the next electron would go into this one to fill up that empty space that chromium had here. And then you'd start adding electrons across the d orbital. When you get to 9, 2, 4, 6, 8, 9, it's copper, and it's in group 9 of the periodic table. It's actually, the number is 1b on the periodic chart. I'll show you why in just a second. And so copper would have this configuration is what we expect it to have. It should have one unpaired spin, and indeed it does. But the unpaired spin, an unpaired spin in a d orbital is a little different amount of electrical charge than an unpaired spin in an s orbital. And so the weight gain is different if you had the unpaired spin in the s orbital than it would be if the unpaired spin was in the d orbital. In this case, this wrong configuration, it turns out, has the one electron in the d orbital, and that doesn't give you the mass change when you weigh it like you get in the real case. And in the real case, what's going to happen is the same thing as before. I'm going to move this electron over to here. Now, logically, why would that be good? Over here, this orbital is filled, but this one has a vacancy in it. And it has a lot more orbital space. You know, there's 5 orbitals here instead of 1. So if I've got a choice of making this one filled or filling this one works better. And it's just exactly what we saw in the copper family. We're going to wind up being, by putting that one electron from here over into here, I'm able to fill this bigger, it's got 5 orbitals, and all 5 of them are full. I'm left with one over here that's half filled. Okay, that's good. I've got a filled and a half filled shell in copper and its family. And again, so make a note and watch for that. Again, that's also either the chromium family or the copper family appears on almost all standardized final exams over this subject. And so you need to remember, make a little star or something on your periodic table over chromium and copper, and remember that all of those are the unusual form. Okay. And then this is what we observe. Now, we've got a half filled and we've got a filled shell. And that is better than the configuration of having the 4s full and the 3d with one vacancy in it. Now, here's a checkpoint on this. And so let's go through this, and then maybe we'll take a little breather and come back. Okay, so fill in the electrons. Now, I'm going to do the one that's I've got here on the TV screen or the computer screen. I think I changed it on the D2L one. So you can work on your own on the D2L one, and if you have questions about it, just email me. But if I had iron, iron is element number 26, and I want to write the, okay, well, let's do iron. Let me get my periodic chart and be sure I remembered the element number for iron. Yes, it is 26. So what am I going to do? I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm going to put 6 electrons into this one. All of these are going to have 2 spin paired ones. I'm going to put 6 electrons into this one. Where would they go? First one goes here. 1, 2, 3, 4, 5. The 6th one would go back here and pair up. So this orbital is going to have 2 in it. This one's going to have 1. 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 These 2 are spin paired. There would be 4 electrons that would be unpaired in this. Now, the last electron would be the one that I put in paired here. So the quantum numbers for it, let's get them. 3, 2, plus 2, spin down would be minus 1/2. 3, 2 plus 2 minus 1/2 would be the last electron that's written out. Now, if I'm looking at the periodic table, and you ought to have one that you can look at, it's on the inside front cover of your textbook, or print the one from the from D2L, so you can have it with you. But I'm looking at iron. Iron is in the you know, I can do this over here and let you see what I'm doing. It may be a little better. Let's stop sharing for right now and go over and look at the camera. Okay. Now, ooh, I've got the wrong camera on, don't I? I want to change to the Logitech webcam. So again, the focus is not real good. Hopefully over this weekend, I can get everything updated. But iron is this element right here. Now, to do the noble gas core idea, you go iron, you go up above it and all the way to the right and look at what that core is. Well, iron is here, so argon is its core. So it has an argon core, and then after the argon core, we're going to go into the row that's got iron in it, and it's the 4th row on the periodic chart. So that's going to be 4s2 when I get to calcium. Now, the first row of d orbitals is the 3d set. So it's 3d is going to have 1, 2, 3, 4, 5, 6, like we said, for iron. And so it's going to be argon, 4s2, 3d6, but broken out into 2, 1, 1, 1, 1. So that it's got 2 electrons in the 3d plus 2, and it's got 1 other electron in each of the other d orbitals. The 3d plus 1, 3d 0, 3d minus 1, and 3d minus 2 are going to each have 1 electron in them. So that's how we could go about. And while we're here, you pick any element on the chart and you want to do that noble core method, we don't need to go through this big stack of energy levels to get to that. All you got to do is do the same thing we did there. There's ruthenium. Well, what would ruthenium look like? Go up a row and over to the end. The end element there is krypton. So it's a krypton core. And then we're going to follow the yellow brick road all the way from krypton till we get to ruthenium. So what would we do? That's row 5. So when I get to strontium, that's 5s with 2. It's the second row of d orbitals. That was 3d. This is 4d. It's going to always be 1 less than the row number. So 5s2, 4d, count them over. 1, 2, 3, 4, 5, 6 would be the same as iron, so it's going to be the same configuration. I didn't notice I did that, but that's okay. Now, let's pick something down here further on. Let's suppose I'm doing osmium. That would be that element right there. It's element number 76. You're following with me on the periodic table. You go up a row all the way over to the end, and that's radon as its core. And then we go from radon all the way over to osmium. So we're going across this row on the periodic chart. That's 6s with 2 when we get to barium. Then if this is 6s, this row is 5d. But watch out. 5d is 57. Hafnium's not 58, it's 72. Where's 58? It's down here. So I'm going to do 6s2, 5d plus 2 is going to have 1 in it. Then I'm going to go around here and I'm going to do the f orbitals. This first row is 4f. So that's going to be 4f, count them all the way over to there, it would be 14. So that's a filled orbital, so I can write it as 4f14. Then I come back up here. Again, I'm in the 5th row. at hafnium. So I'm counting over to osmium. 1, 2, 3, 4, 5, 6. So I'm going to put 6 electrons. I did it again, didn't I? I'm going to put 6 electrons in the d orbital, and I'm going to get the same kind of configuration I got for iron and that I got for ruthenium. But I wanted to show you, if you get past element number 57 on the periodic chart, you're going to go, the next element is going to go down here and across the row before you get back up there. So you don't want to forget these in there. You also need to notice that when I go like that, like when I get to lithium, lanthanum, I'm going to have, in the 5D set, I'm going to have 1. D orbital, first orbital to fill in the D set is +2. So I'm going to have a 5D +2 with 1 in it. Then I'm going to go down here and do the others. So if I'm stopping down here somewhere, don't try to put all those electrons in the F orbital. Remember, one of them is up here at lanthanum. It's the rest of them that go down here. So if I'm down here at, okay, what would be a good one? Europium. Okay, so I'm going to say, well, what would europium be? It's element 63. So I'm going to go over here and look at the noble gases. And the biggest one that's less than 63 is xenon. So its core is going to be xenon. And then I'm going to do 6s2, 5d +2 with 1. And then I'm going to go down 1, 2, 3, 4, 5, 6 for europium. And it's going to have 6 electrons in the F orbital. Now remember, F is 3, so they're going to be +3, +2, +1, 0, -1, -2, -3. And I've got to put 6 electrons in, so I'm going to just go across that list and put 1 in each one. And then that would be the orbital designation for that. So we can get the orbital designation, get the number of unpaired spins, get the understanding of the chemistry without having to put for europium 63 electrons in that stack of orbitals that we had. So do practice doing that. Okay, whoopsie daisy. No, I still want to go to share screen, and we'll go back to here. Okay, so we have been way down here, and okay, I think this would be perhaps a good time to take a little bit of a break. It's what, 5 till 9? What, maybe 10 minutes? Maybe we'll start out at 9. We'll come back at about 9:05, and go on from there. So I'll see you in about 10 minutes. I'm going to pause the recording so we don't. And then we need to go back to our screen. And okay. Ooh. Didn't share screen. Okay, let's get the other one. I think that's, I gave it that one. All right. And now let's go here. All right. Okay. Oops. Now. All right. Now, we're looking at, again, taking what we've just learned about how the atom is made up. And now remember what we've got. We've got a nucleus. We've got a noble gas core. Then we've got partially filled shells outside the core. And those partially filled shells are going to be what determines the reactivity and the nature of that particular element. Now, so this is what our model looks like. I've left out the nucleus because it's really not important chemically at all. Only thing it does is tell us how many electrons are going to be out here. This core of electrons goes as a group and is seldom, if ever, changed during the course of a reaction. You're not going to take electrons out, and you're not going to put electrons in to that core level. The outer layer we call valence electrons, and we've seen now the type of orbitals that they might be in. And this group of valence electrons could be more than one particular set of values. Like, for example, the 4s orbital in the transition elements would be the outer part of that. And then the 3D level under that would be a part of the valence shell. It's outside the core. It would be a part of the valence shell for that element, but it wouldn't influence other things very much because the 4s electrons are further out, and they're going to be the first thing encountered. So we're going to try to develop a way of illustrating this. We're going to call that Lewis dot structures, and we'll get to that in a minute. So now, for the 1s orbital with 1 in it, that's hydrogen. And the second electron is helium. It's the noble core. The next one was lithium, then beryllium, then boron and carbon and nitrogen and oxygen and fluorine, and then neon, and then sodium. And now the gap that I'm leaving in here are the transition elements. And the ones that I'm showing you that very regularly, 1, 2 electrons, then 3, then 4, then 5. That group is the group A elements called the representative elements. And you maybe see why they're called representative elements is because their electron configuration is easily understood and represented by the arrangement on the periodic chart from this orbital designation. And we can go on with the elements like that. So all of these elements have a core and then NS1. And this one is N equal 1, N equal to 2, and N equal to 3. So a group 1A family looks like that. They'd all look just like that. And you'd have a core, and you'd have 1 electron on the outside in the core. So we're doing what we call Lewis dot structures. And the Lewis dot structure has the symbol for the element and then 1 dot somewhere around that symbol. That would represent any of the elements up here. Any of the elements in that family would have that type of orbital designation and would give rise to this. Like if it's lithium, it's Li with 1 dot, or sodium is Na with 1 dot, and so forth. If I'm going to this family, then what I'm going to get is a core with NS2. The only thing is changing is the N value here is 2, and then it's 3, and then it's 4. For all the elements in that family would look like that. If we want to see what the picture looks like, they're going to have a core with 2 electrons in it, and notice they are paired up. So when I go to this kind of structure, I want to show the symbol like Be with 2 dots, and they have to be paired up. I don't want one of them over here and the other one somewhere else over there. Now, they could both be over here, or both over here, or both here, or whatever. The important thing is the symbol with 2 dots right next to each other, showing that they're paired. Okay. And when I go to group 3A, then they're going to have a core. NS is 2, NP is 1. So they're going to have 2 and 2, and 2, 3 and 3, and so forth, for all of those elements in that family. And the picture would look like this. You got a core, you've got a s orbital with 2 electrons in it, and you got a p orbital with 1 electron in it. And these two are paired up, but this one is not paired with that one. So you want to do the symbol like this. Now, it doesn't have to be, the Lewis dot structure doesn't have to be exactly like I've drawn it there. What it does have to be is it does have to have 2 of the electrons that are obviously paired together and 1 that's not. Does that one need to be there or there or there? It could be anywhere as long as you've got 2 paired up and 1 unpaired. That tells us what the group 3A family looks like and the way they react. And then we do the same thing with the group 4 elements. You've got the core, and then you've got the 2s or the s2 configuration and p1 and p1. So you've got 2 of them paired up, but these 2 are not paired. That's why it was important that we write them the way we did rather than NP2 like this. This NP2 looks like both of them are paired up, but they're not. See, they're down here, one in this orbital and one in that orbital. So the Lewis dot structure has to look like this. Of the 4 electrons, 2 are obviously joined together. They're paired. But the other 2 can be anywhere. I've joined it here and here. It could be here and here, or it could be here and here. The only thing that's important is that there's a pair here and 2 oddballs, 2 odd ones here. And then nitrogen is going to be like this. Nitrogen is going to have, all of these elements are going to have 3 in the p orbital, means you've got 1 in all 3. That third p orbital would be coming out of the screen. That's why I didn't try to draw a 3-dimensional figure for it. But it's got 1 electron in each of the 3 p orbitals and 2 electrons paired up. So again, we can have 5 electrons in group 5. 2 of them are paired and 3 are not paired. Where do the pair go? It doesn't matter. I could put them both here, and that I could put 1 here to pair up and leave 1 open there. I could put the pair here or here. You can put the pair anywhere you want, but it is important that the figure look like 2 of them are together, paired up, and 3 of them are not paired up, however, wherever you put them. And then when we get to the next one, we're going to do P4. P4 configuration, remember, you put the first 3 electrons in, the 4th one has to pair up with 1 of those. So that means you're going to have 2 paired in the p orbital and a pair in the s orbital and the others unpaired. You've got a total of 6. So if I'm going to do this, I might do 1, 2, 3, 4, 5, 6, like that. See? 1, 2, first 2 are paired. 3 goes somewhere. 4th one goes somewhere else. 5th one goes somewhere else. 6th one pairs up with 1 of the others. It could pair up here or here or here. It doesn't matter. But what does matter is 2 obvious pairs and 2 obvious unpaired electrons. That's important. And you're going to see why very, very shortly. In fluorine, we're going to have 5 electrons in the p orbital. The 5 are going to be grouped as 2 paired and 2 paired and 1 odd. So it's going to look like that. And again, if I'm doing it, let's say I start here. First electron goes here. Second one goes paired up with it. Third one goes in one of the p orbitals. 4th one goes in another. 5th one goes in another one. 6th one pairs up with 1 of those, and the 7th one pairs up with 1 of the others. So we've got 3 obvious pairs and 1 lone electron. And of course, the noble gases, they're all just 4 pairs, 8 electrons on the outside for any of the noble gases except helium. Helium is just going to have 2, but that's all it could have in the 1s orbital. But you can have 8 in all of the rest of them, and you do. 6 and 2 and 6 and 2. So they would all be 8. We don't usually draw Lewis dot structures for the noble gases because they don't react. Typically don't react. Okay, so this is the way we draw Lewis dot structures for any of the elements on the periodic chart. Here's a, well, I want to back up and make a point while we're here. Let's look at what could happen to these elements. You can have an electron lost, +1. You can have 2 electrons lost, that's group 2. You can have 3 electrons lost, that's group 3. 4, group 4, 5, 6, and 7. That's the group numbers on each one of those columns of the periodic table. The metals elements tend to lose electrons. And that would give you this kind of, we can predict the charges for the metals as being just losing all the electrons. You see it. If I'm looking at group 6, then I could lose all 6, and that would give me a symbol which would represent a noble gas core under that. And then that would give you the correct charge for group 6 and the metals, and the ones near the bottom of the column would tend to do that. Ones near the top would probably not. They would gain electrons. And you can look at this Lewis dot structure and see how many you should gain. If I'm in group 7, I need 1 more to pair that up, and then I'd have 8 on the outside like a noble gas. So all of these will gain an electron. The electron's negative, so all of this family is going to be a -1. I can look at this. I could gain 1 here and 1 here to fill that out. There'd be -2 for oxygen in this family. Then I could gain 1 here and here and here. It would be -3 for everything in this family, and so forth. You could get a negative charge, a negative ion, by adding electrons to fill out. Now, you look way over here. Is it likely group 1 is going to pick up 7 more electrons to get 8 around it? I don't think so. No, it doesn't. It could get to a noble gas much easier just by losing an electron. So the metals tend to have the positive charges, and we can predict what it is. The non-metals tend to have negative charges, and we can predict what the negative charge is by seeing how many more electrons I have to add to get 8 on the outside. And so I get 1 here, and 2 here, and 3 here, 4 here, and so forth. We'll make some more points about that later, but I thought this was a good time to see why this is important. Okay, let's do the Lewis dot structure for selenium. So if I'm looking at selenium, I'm not going to change the camera around, but I'll look at selenium myself on the periodic table. You can look with me if you want to. Selenium is in group 6A. It's element number 34. So if it's in group 6, I'm going to put electrons around, and I'm going to imagine, okay, let's go here. There's 1. The second one pairs up. 1, 2, 3, 4, 5. Now I need to pair up 1. 6. I'm going to have 2 pairs, 1 pair here, 1 pair here, and 1 oddball here and here. So that's what group 6 is going to look like. And so that is the, gives a symbol for an element that has this one. Well, hey, that's pretty easy to do. I got 1, 2, 3, 4, 5 to put in. That's in group 5. Okay, so what the answer to this question? Anything that's in group 5 would be okay. It would have an electron configuration like that. Okay, that's really all we need to do now. And we are quite a bit ahead, as it turns out, in the lecture for our quiz. I think if I remember the syllabus right, the quiz is like Tuesday of next week. So I'll look again and be sure, but we've covered essentially everything that's on quiz 1. We'll go over the practice quiz and do a lot of review if we got time. I don't want to really work real far ahead. but I will keep I'll keep the syllabus schedule for the exams and quizzes. I'm going to try to be rigorous about that. But if we get extra time, we'll just use it for review and discussions. Okay. All right. So that's the end of that one. And let's stop that share and stop that recording.